We've mentioned several times the terms gland seals and steam sealing strips. It's time for us to take a closer look at these. When we consider that the rotor is turning at high speed, it is obvious that some clearance must be provided for the shaft as it protrudes from the stationary casing at each end of the turbine. Now remember, there is very hot steam at substantial pressure inside the casing at the high pressure end of the machine. So there is the potential for a considerable amount of this hot steam to leak out through the space between the rotating shaft and the casing. And would we not have the same condition at the low pressure end? Well, yes, if this is a back pressure turbine with a positive exhaust pressure at, say, 50 psi or over. Although the pressure and temperature is less, there would still be leakage between the casing and the rotating shaft. But what about the case of a condensing turbine? Well, in this situation, there is a vacuum inside the casing at the low pressure end. So instead of steam leaking out, air would leak in, and we do not like that either. It could lead to a loss of vacuum and consequent loss of efficiency. In order to reduce this leakage as far as possible, gland seals are located at each end of the casing. The aim of the seal is to provide a high resistance to the flow of steam or air. This is achieved by the use of a labyrinth seal. The rotating portion on the shaft is slotted like this, while the stationary portion consists of thin metallic strips which are pressed into the rotating grooves by very light spring pressure. The resultant labyrinth path considerably reduces the leakage of steam out or air in. Even so, there will still be some leakage of steam at the high pressure end through the gland seal. This leakage steam is extracted from the gland and fed into a low-pressure extraction point. The leak-off valve automatically adjusts the pressure within the gland steam header to maintain approximately 5 psig. But even at that low pressure, there will still be some leakage along the shaft into the turbine room. In order to prevent this steam from getting into the turbine room, it is drawn from the outside of the gland seal by a slight vacuum, which is produced by the gland steam exhauster. Some heat is recovered from this small amount of steam, bypassing it through a heat exchanger in the condensate system known as the gland steam condenser. Now let's see what's happening at the vacuum end of the turbine. Well, we definitely do not want air to enter the casing, even the small amount that may flow across the labyrinth seal. In order to prevent the leakage of air into the casing, low-pressure steam is provided from the header to the low-pressure gland seal. This results in a small amount of steam entering the turbine casing, and this is far preferable to air. Of course, some of this will try to pass along the shaft in the opposite direction to atmosphere. But this is captured by the gland steam exhauster in the same manner as for the high-pressure gland seal. So we can see that leak-off steam from the high-pressure end is useful in providing sealing steam at the low-pressure end. As the load changes, the leak-off valve opening adjusts to maintain the appropriate header pressure. But how does the system work when we're preparing for startup? In this situation, we need to pull a vacuum in the turbine and condenser before admitting any steam into the turbine. So in this condition, we have no leak-off steam. Instead, live steam is supplied to the gland steam header. The live steam supply valve is set to control the header pressure at about 3 psi to coordinate its operation with the leak-off valve. When the turbine comes on load, the leak-off steam from the high-pressure gland feeds into the header and so raises its pressure. When the pressure gets to 3 psi, the live steam supply valve will close. When the pressure rises to 5 psi, the leak-off valve will open enough to maintain this pressure. Remember that there are two basic circuits in the gland steam seal system. First, the gland steam header, which supplies steam to the seals or dumps excess steam. The second circuit extracts leakage steam from the extremities of the glands and passes it through a heat exchanger and the gland steam exhauster. Make sure to check and learn details of your own gland steam system. Sealing strips are similarly used in other parts of the turbine where we need to eliminate or at least reduce steam leakage. A typical example is the interstage seals, which are inner circumference of the diaphragms where the shaft rotates. In all cases, the seal strips are made of very thin, soft, metallic material. They rub on the shaft and reduce the leakage as much as possible. Of course, as time passes, the sealing strips wear and need to be replaced during regular maintenance. We'll be discussing this aspect in another module in this series. Well, so much for sealing systems. Another very important support system that is essential for turbine operation is that of lube oil and hydraulic oil supply. The lubricating